So let's describe how metals bond with other metals. And to begin that conversation, let's once again go to the periodic table and look at the electron configuration of these elements. So here's our periodic table. Our metals are the ones that live on the left side. Let me highlight some for you. Grab the right pen here. Good. These are our metals. All of these are metals. So the vast majority of the elements that are known are metals. Now let's look at this a little bit more closely and remind ourselves what they have in common. Now when we zoom in and we take a look at the electron configurations, I should say, the electron configurations, the valence shell is very low. Let's take a look at some more. Let's slide this over. Still in the realm of our metals, valence shells are very low. And I want to slide over and get over to copper. Copper. Valence shell has 1 electron. Nickel, 2. Cobalt, 2. Iron, 2. And what this means is they have, well, a very weak affinity for electrons. So their electronegativities are low. Let's grab a pen here. So if we have an example of copper, as I said earlier, copper, it has 1 valence electron. Let me just double check. Was that 1? Yes, it was 1 valence electron. And again, that means that this element does not want this last electron. It wants to lose it. Well, if in fact copper comes in contact with other coppers and even more coppers, what will happen is they all do not want their outermost electrons, and they tend to stick together, in a sense, bonding. So that's where we get our term metallic bonding. And keep this in mind as well. If they're all copper and they're bound together, I don't care if it's copper with with 2 atoms, copper with 15 atoms, copper with 15 trillion atoms. The fact that they're all copper atoms means that it is not a compound. It is still an element. So its name would just be copper. Alright, so let's take a look at some more. So here is magnesium. It's got an electron configuration of 2, 8, 2. Let's write this down. Magnesium is 2, 8, 2. It likes to have 2 valence electrons that then like to leave. Okay, magnesium will bond with other magnesium, forming a big collection of magnesium atoms that are bound together. We're going to zoom in and take a closer look at that in just a moment. So once again, I said that they will collect together, okay, to form a collection of bonded atoms. So let me write the magnesium here again. It's 2, 8, 2. And we said that these outermost electrons will like to leave. So we have a way that we could represent the magnesium, its nucleus with the neutrons and protons, and these inner shelled electrons. Now all of that together would be called something like a kernel. Not the one you salute to. A kernel meaning the nucleus with its plus charges and its neutral charges, all of them. I'm not going to draw them all. With those 2 inner shelled electrons, we have 2 here and 8 here, and then those 2 electrons that would like to go somewhere else. This portion here is called the kernel. Our next illustrations are going to show you what it looks like when they're all together. So here's one of those illustrations. This positive sign, it represents what's left when those valence electrons leave. So it is the ion of the metal. So it's representing the protons in the nucleus, the neutrons in the nucleus, and the inner shelled electrons, all being represented by that positive circle. And here we have these free electrons. And we use this term, as well as a few others, as mobile valence electrons. It's also sometimes called a sea of mobile electrons, or even delocalized electrons. And, well, this is just one picture. Let's take a look at another. So here's another illustration entitled Metallic Sea of Electrons. Now the positives in the middle, again, are the kernels. And these cloudy areas here are those mobile electrons. And it states down here, electrons are not bonded to any particular atom and are free to move about in the solid. It's just not saying in what direction they're free to move. Here's another illustration indicating, again, our kernels. They're calling them, let's move it so you can see it, metal cations, which should make sense to you by now, and identifying our sea of delocalized electrons. So they are free to move wherever they would like, and I wrote those terms down for you here so you could get those into your notes. So sea of mobile electrons and delocalized electrons. They mean the same thing, but be prepared to hear them both. Which brings us to identifying why metals are great conductors. This again will have to do with those electrons. So here's a great picture, similar to the ones in the past, to help us understand this. Now, here we have our kernel, and here are the electrons. The electrons are free to go in any direction they want. Think of it as these kernels do not want their children. Well, if this one doesn't want it, and this one doesn't want it, and this one doesn't want it, they're free to roam the neighborhood as they wish. But it gives it the quality of a good conductor when we use that analogy for metals. So we have over here picture B, C, and D. And what this is trying to show you is how the electrons can move on. And if in fact let's just say this is about electricity, if we start adding electrons to that end, and we keep on flooding electrons to this end, well, we are going to force them to go in one direction. We are going to force them to go in that direction. Now think of it as a garden hose. If you start putting water in on one side of the hose, it's going to flow to the other, like current in a stream. And that's why we get the term current when we talk about electricity. So, electricity is truly a flow of electrons through a wire, which explains our next picture. Which explains very nicely why copper is chosen for electrical wire. But be cautious. That current can also travel through you. Alright, let's take a look at pots and pans for a moment as well while we're at it. So pots and pans too are produced by metals. It doesn't make sense to make them out of plastic now, does it? Well, the energy that is going to be placed at the bottom of the pan will force the electrons to move around quickly, transferring the heat to inside the pan. Not to mention, remember the qualities of metals? Let me just write them down on the next slide just to remind you at this moment. It's a good idea to get it down now. So remember, another reason why metals are good to form wires and pans and so forth is because they are malleable. Malleable means that they could be struck with a hammer to change its shape. They are ductile, which means they could be pulled into a wire, and they are good conductors. Now they also have luster, but luster does not assist with this discussion, but it is also good to remember that it does carry that quality. So that's all about metallic bondings. Good luck with every question you see about it.